Thank you and welcome to Heatsink 101, an introduction to heat sinks. Topics that we will discuss include what is a heatsink, a brief heat transfer review as related to heat sinks, which includes conduction, convection, and radiation. In addition to heat transfer, we will discuss other factors that influence heatsink design. Finally, we'll discuss an application example based on the Karma board from the California Institute of Technology for use in the Owen Valley Radio Observatory. A heatsink's purpose is to allow for more efficient heat transfer from a heat source to the surrounding fluid and environment. Whether the heat is convecting to the fluid passing over it or radiating to the surrounding environment, the surface area is a key factor for efficient heat transfer. It is worth stating that heat flows from higher temperatures to lower temperatures and only transfers when there is a temperature difference. Efficient heat transfer implies that the heat is transferred at a smaller temperature difference. For a heatsink, heat moves from the source, which is the die in the component shown, and conducts through the component into the heatsink base and fins. From the surface of the heatsink, heat leaves through convection and radiation. Generally speaking, heatsinks are made of a high thermal conductivity material, such as aluminum, for efficient heat conduction, and maximize the surface area for efficient convection and radiation to the environment. Heatsinks come in many shapes and sizes, with a few varieties shown here. The upper left is a plate fin heatsink and is the type of heatsink we will focus on primarily. In the upper right is a pin fin heatsink, which has advantages over plate fin for some scenarios that we'll discuss later. In the lower left is a heat spreader that uses heat pipes to efficiently move the heat from the spreader to a fin stack that presumably is located in an area of forced air at cooler temperatures. The last heatsink in the lower right is an active heatsink. It has an integrated fan that supplies its own source of high-speed air to transport the heat away. Let's discuss some of the factors that influence heatsink thermal design. At the device level, there are factors such as component power dissipation and maximum junction temperature. The more heat the component dissipates, the more effective the heatsink needs to be at removing it to maintain the maximum allowed junction temperature. Thermal interface material, or TIM, and IC package style affect the temperature rise from the die to the heatsink base. Higher thermal resistances will require the heatsink to compensate for the additional temperature rise. The system this heatsink will be used in has an equal part in determining the heatsink requirements. How much space is available? What is the ambient temperature of the fluid passing over the heatsink? What is the elevation? Arid elevation is less effective at heat removal. Is the heatsink exposed to forced convection flow from a fan or natural convection where the hot air rises due to buoyancy? Is the system such that the forced air can easily pass around the heatsink rather than between the fins, making the heatsink much less efficient? There are also some practical considerations. The heatsink has to be manufactured, ideally at a reasonable cost. Reliability might also be an issue, which may mean that an active heatsink or a heatsink with an integrated fan that could fail might not be a good choice. The primary focus of Heatsink 101 are plate fin heat sinks and forced convection, but there are a couple points to make about natural convection before we move on. First, consider the orientation of the heatsink when placed in the system. Is it aligned with gravity? If gravity isn't aligned with the plate fins, then a pin fin heatsink is probably a good choice. It does sacrifice surface area, but ensures that the buoyancy-driven flow has a pass through the fins. Second, in natural convection, radiation heat transfer is much more significant than in forced convection. It's common to ignore radiation heat transfer in forced convection heatsink thermal design. It's a conservative assumption. When radiation is significant, the heatsink will benefit from a higher emissivity. When determining the thermal requirements of a heatsink, it's useful to think of heat transfer in terms of thermal resistances. Let's take a minute to review thermal conduction and convection in terms of thermal resistances, which are typically shown in terms of temperature difference per unit power. For conduction, this translates to L over Ka, or the ratio of the material thickness and the thermal conductivity times the cross-sectional area. For convection, the thermal resistance is 1 over Ha, or the inverse of the heat transfer coefficient times the surface area. Let's use that idea of thermal resistances and develop the thermal budget, which is a common approach for estimating the thermal requirements of a heatsink. The delta T budget is the difference between the maximum allowed junction temperature and the ambient temperature. For the Q, we'll use the power dissipation of the device. As a conservative assumption, it is assumed that all the heat flows into the heatsink base. The first thermal resistance is the junction to case thermal resistance of the package. For a typical CPU, this value will be in the range of 0.1 to 1 Kelvin per watt. The next resistance along the path is RCS, or case to sink thermal resistance, and the thermal resistance associated with the interface material and mounting method. Values for the thermal resistance in the TIM layer are usually presented in terms of thickness, which is referred to as bond line thickness, and thermal conductivity, or the ratio of L over K. The interface between the component and the heatsink is commonly referred to as the TIM2 layer and has typical values ranging from 0.1 to 1 degree C inch squared per watt. The last thermal resistance is RSA, or sink to ambient thermal resistance, and is a function of the heatsink thermal design. Before we discuss the thermal design of the heatsink, the sink to ambient thermal resistance, let's discuss some of the relevant aspects of thermal interface materials. Thermal interface materials come in a variety of forms. I have categorized them in terms of pastes, phase change material, thermal adhesive, and thermal pad. Important properties of TIMs include the bond line thickness, the bulk thermal conductivity of the TIM, and the contact resistance at the wetted surfaces. Those parameters define the overall thermal resistance of the TIM. Other important considerations include the associated required pressure to achieve a bond line thickness and the ability to rework the material. The interface material may also have implications on reliability, as the overall thermal resistance may change over time. Some TIMs offer mechanical strength, as in an adhesive, but many do not. TIMs that require other methods to secure the heatsink in place typically offer better thermal performance. Though thinner bond lines will offer lower thermal resistances, there are situations where a thicker interface material is needed. One example is to compensate for variances in component height for a heatsink mounted on multiple components. The last comment on interface materials is that when designing a heatsink, we use values offered in a datasheet, but the only way to truly know the thermal resistance across the component and the heatsink is through measurement. The next thermal resistance in the thermal budget is the sink to ambient thermal resistance. There are two components to the heatsink efficiency: conduction through the solid and convection and irradiation to the surrounding. We'll start by looking at the efficiency of heat conduction within the heatsink. Ideally, the heatsink is at a uniform temperature. In reality, this isn't possible. A temperature difference is needed to move heat. The temperature difference, or gradient, across the heatsink base and fins is an area of focus, though. Higher gradients will result in a less effective heatsink design. One heat conduction inefficiency is spreading resistance. Anytime there's a cross-sectional area change in a heat conduction path, there is an associated spreading resistance. An additional thermal resistance beyond that due to the bulk thermal conductivity and the thickness of the material. The situation is quite common as heat is conducted from the TIM2 layer into the heatsink base. Determining the spreading resistance is not trivial though, and two resources are provided. The first, from the University of Waterloo, is an online calculator for determining the thermal resistance for a number of different geometries. The second link is to a paper from Song, Lee, and Oh, which provides equations for estimating the thermal resistance and is very useful in a spreadsheet application. Let's take a look at how spreading resistance affects the heatsink thermal design. Consider the example of a heatsink on a component in forced convection. Flow therm was used to vary the heatsink base thickness. The material thickness affects the spreading resistance, while maintaining the overall heatsink height. So as the base thickens, the fins get shorter, so the overall height is maintained at 10 millimeters. The sink to ambient thermal resistance is plotted versus the heatsink base thickness. Temperature plots of the heatsink base are shown for the initial design and that of the optimal design. Both plots are shown on the same temperature scale, so adding 1 millimeter to the heatsink base thickness resulted in a much smaller temperature gradient in the heatsink base and resulted in a better heatsink thermal performance. As the heat conducts into the fin, there is also inefficiency loss due to the temperature gradient, which is known as fin efficiency, and is the ratio of the actual heat transfer rate and that if the fin was at a uniform temperature. The formula shown is based on the assumption that the fin tip is adiabatic. The plot shows the fin efficiency versus fin thickness for fins at two heights and two heat transfer coefficients. The fin is assumed to have a thermal conductivity of 200 watts per meter Kelvin. The plot shows that at higher heat transfer coefficients for longer, thinner fins, the efficiency is lowest. For heatsink thermal design, fin thickness and material, looking at copper versus aluminum, could be considered to address this. Now let's take a look at estimating the thermal resistance associated with convection from the surface of the heatsink. Though heat conduction is a contributor to the overall performance of a heatsink, the thermal resistance associated with convection is the dominant factor when estimating the performance. For initial sizing of a heatsink, it's reasonable to only consider the fin area and the heat transfer coefficient. Typically, the Nusselt number correlation for laminar flow over a flat plate is used to estimate the heat transfer coefficient for a plate fin heatsink. A simplified expression is provided for estimating the heat transfer coefficient as a function of the velocity and fin length, assuming the fluid is air. So this equation is based on the definition of the Nusselt number and the Reynolds number for a flat plate, the Nusselt number correlation for laminar flow over a flat plate, and the properties of air at 300 Kelvin. Recall that the convective thermal resistance is 1 over HA, and from the thermal budget we know roughly what this value needs to be to maintain our component temperature. From that and our estimate for heat transfer coefficient, we can estimate the surface area requirements for the heatsink. Before we can think about the surface area of the heatsink, we need to consider the effects on flow impedance. For a heatsink on a component on a board, there is an opportunity for the flow to bypass or to go around our heatsink rather than through the fins. Heatsinks with larger fin spacing will have higher velocities in the channel, but would have lower surface area. Smaller fin spacing would lead to more bypass, which means lower velocity in the channel, which translates to a lower heat transfer coefficient, but more surface area. For each design scenario, there will be an optimum number of fins or fin spacing. There is an infinite amount of combinations of fin heights, number of fins, and heatsink base dimensions that could satisfy the surface area requirements. So where do we start? One place to start is with the assumption that the flow in the fin channel is developing and isn't fully developed until it reaches the exit of the fin channel. When the flow enters the channel, a boundary layer begins to develop on each plate, as shown in the image. The flow is fully developed when the boundary layers from each plate merge. As the flow is developing, the fin will have the maximum heat transfer rate per unit length, but also the highest pressure drop per unit length. When the flow is fully developed, these values remain constant. The equation shown provides an estimate of the fin spacing given the length of the fin in the flow direction and the approach velocity. This isn't necessarily the optimal fin spacing, but does provide an estimate. With this value, along with the fin length, you can estimate the fin height required for a number of fins or the number of fins required for a specific fin height. Again, this provides a starting point to understand what physical size a heatsink may be required. Up to this point, we have reviewed the heat transfer modes for heatsinks, some of the design considerations, and a methodology for determining the thermal requirements of a heatsink with the thermal budget. We also introduced two equations that can be used to estimate the thermal performance of a plate fin heatsink. Equations like this are a good starting point for new design, but there are a number of different approaches for heatsink design that each have advantages. Let's compare different approaches with respect to speed and accuracy. Generally speaking, there is a reduction in speed when there is a gain in accuracy. The first method we will consider is hand calculations or spreadsheets. Certainly this would be the fastest approach and can be tuned to be more accurate by adjusting the correlations based on in-house test results. The speed is essentially instant as you test various inputs. This approach is typically used as a starting point, but not necessarily to qualify the final design. The next approach is finite element analysis, or FEA. This would be a 3D numerical analysis that would have a high degree of accuracy on the conduction heat transfer side, but would require the use of heat transfer coefficients based on correlations. The next approach would be computational fluid dynamics, or CFD. This method would be more accurate than finite element analysis since it would solve the Navier-Stokes equations with conjugate heat transfer. Fewer assumptions would need to be involved than with FEA. I estimate that there wouldn't be any speed difference between FEA or CFD. The most accurate, but possibly the slowest, would be a lab test. A lab test does require a physical heatsink to test, so we have to consider the time it takes to manufacture the prototype. Lab tests should always be part of the process, but primarily used as a design validation at the end of the process. There are tools like Flowtherm that are CFD tools specific for electronics cooling. With Flowtherm, there would be a speed up over general CFD as you could build and solve the model more quickly. Flowtherm also has built-in design optimization capabilities, so many heatsink variants can be studied and optimized automatically. Also, the MCAD and ECAD integration, along with detailed IC package modeling, allows for more accurate prediction over general CFD. We'll take a closer look at how these capabilities of Flowtherm can be used to optimize a heatsink design. The example we'll be looking at is based on the Karma board thermal design for the Owen Valley Radio Observatory. Let's start by looking at the device, system, and practical design constraints. The objective is to design a thermal solution for U-136 through U-139 that maintains the junction temperature below 95 degrees C. But also, these operating temperatures need to be within 5 degrees C of each other. 13 watt power dissipation is fairly low, so a high performance TEM won't be required. We will assume a value of 1 degree C inch squared per watt. And also, the IC package is a flip chip BGA and has a junction to case thermal resistance of 0.1 degrees C per watt. So this information could be used to determine a thermal budget and kind of estimate the size of the heatsink, but we're going to include this information directly in our Flowtherm analysis. So the Karma board will be placed in an enclosure with the printed circuit boards on a 0.8 inch pitch. So this is going to constrain the height of the heatsink to about 12 millimeters in this case. There are also neighboring components that will limit the length and width of each heatsink. At a 35 degree ambient, it's lower than the typical 55 degrees C that we designed too many times. So that's going to work in our favor. We will, however, be designing this for use at a 10,000 foot elevation, so we'll include the properties of air at 10,000 feet in our Flowtherm analysis. And we see the approach velocity is 400 feet per minute. The practical constraint of a single extrusion requires that all heat sinks have the same thin thickness and pitch. Since these components only dissipate 13 watts, we should be able to design a light enough heat sink that they could be attached with an adhesive tape that has a thermal resistance of 1 degree C inch squared per watt. Also, at this low power, an active heatsink won't be required. So as a first step in the design, I analyzed the board without any heat sinks. At 13 watts, there was a possibility that no heatsink was needed. As you can see though, all the temperatures were over 130 degrees. It is interesting that U-136 was almost the same temperature as U-139. If all the heat was convected off the components, the temperatures would have increased in order as the air is preheated from the upstream component. In this case, the PCB is acting like a heatsink, and U-136 benefits from not having high temperature neighbors other than U-137, so they're conducting heat into the board, and the heat can then convect off the board, acting like one big heatsink fin. So the next step, knowing that I need heat sinks, was to go ahead and add heat sinks. I chose a heatsink length and width that were about the same size as the components at 37 millimeters, and a base thickness of 2.9 millimeters, which left 9 millimeters of available height for the fins. I used Flowtherm's command center to explore the design with respect to the number of fins, and each heatsink was constrained to have the same number of fins, so each heatsink is going to have the same exact extrusion. It is interesting that each heatsink had a different optimum number of fins, though only one component, U-138 at 5 fins, lied in the target band between 90 and 95 degrees C. The target band is shown with the light blue shading. Operating temperatures below 95 would certainly be acceptable as long as all the components were within 5 degrees of each other. Also, 12 fins for U-139 isn't necessarily the optimum, it's the lowest value for the range that I studied. The strategy for achieving operating temperatures within the design band was to allow each heatsink to have different fin heights, and I chose the number of fins to be 10. The thinking behind that was it's in the range that allowed the leading component, U-139, to have shorter fins than if I had gone with fewer fins. So more fins, they can be less height with the same amount of area, and then that would benefit the downstream components because that leading component would have a lower profile. Also, the most downstream component I thought would benefit by having more fins than less fins to convect its heat away. So after having decided on the number of fins, I needed to study how tall each fin should be for each heatsink. So I used Flowtherm's command center for that. I set up a design of experiments in Flowtherm's command center to vary the heights of all the heat sinks except U-136. I left the most downstream component at fin height of 9 millimeters. So the fin heights, other than the last one, were allowed to vary independently within a range of from 2 millimeters being the shortest to 9 millimeters being the highest. In all, 18 designs were created and analyzed. So this plot shows the fin heights for each design. Notice the distribution of the values across the range. The resulting component junction temperatures are shown in this plot. None of the designs resulted in the components operating within the band, though design 2 came very close. The design of experiments is a great way to study design space automatically, but very difficult to make a design decision from directly. There's a wide distribution of operating temperatures, just as there were a wide distribution of inputs. So the next step in the process was to use Command Center's Response Surface Optimization, or RSO. After doing the design of experiments, I set up some design goals. One was to minimize the difference between the operating temperatures of the components, and I also used an output constraint so that no component operating temperature would exceed 95 degrees C. So the response surface optimization is a mathematical calculation performed by Command Center, and it takes about 20 seconds in this case. And what it returns is the optimal fin heights and a prediction of what the operating temperatures would be. After the mathematical estimate, you need to confirm that prediction with a CFD. So I did that. I ran the CFD analysis based on the RSO recommendation, and I'm reporting the output of that. So the components are very close in operating temperature, and though U136 is reported at 96 degrees C, I believe it to be within the design requirements at this stage of the design. I've included some references for you that may be of benefit, a mix of textbooks, technical papers, and web links. Hopefully you still have your heat transfer and fluid dynamics textbooks. They most likely will have further explanation on laminar flow in a channel and heat transfer from extended surfaces. I enjoyed reading hot air rises and heat sinks and find it to be educational and entertaining for anyone new to the industry. There is also a link to the Karma Board project for the California Institute of Technology. We've covered a lot of ground in a short amount of time, starting from what is a heatsink to optimizing a heatsink design for 4 inline components. There are a number of approaches to performing a thermal design of a heatsink, but only CFD or physical test of the heatsink in the system provides the actual operational performance for your design.